And so we are going to be dealing with vectors that do have direction and magnitude. And that gets us into our idea that we have different types of motion. We have projectile motion. And if you go back and you look at that original basketball toss that we did that basketball toss. And when you plotted your graph, you saw things were moving differently if I was in the X direction or that horizontal direction, or if I was in the up and down motion. I actually had two different things of motion, and those motions were independent. In the X direction, we didn't have an acceleration. In the Y direction, the ball was being acted upon by gravity, and so we did have an acceleration. And so the motion that we tossed the ball up was going to look very much like the upward ball toss that we have done before, or looks very much like your ball drop that you're going to do for your lab. But the X motion that you had, it was moving along at whatever initial velocity it had in the X direction, and you got this lovely straight line that you had with that particular graph data. So you do have that data. So when we're talking about vectors, they have direction and magnitude. And when we're in two dimensions, we have to worry about both the X and the Y. And that also comes into our idea about motion. So I have this little video here. I took my grandsons on a trip. And so I'm going to actually pull up this video here. And we're riding along on a train, and you're going to see that that motion in the X direction is actually independent of the motion in the Y direction. So we have our lovely okapi here. And if, for those of you who do not know what an okapi is a mountain or is a jungle type giraffe. They have very, very soft skins. They have very unusual tongues. They can actually suck their eyes in. So they're kind of a cool critter. But this is my grandson, and we are moving on the train. We are actually standing still and moving on the train. And if I go ahead and play this video, he is going to toss.
Jump.
He's tossing the okapi up and down, and the okapi is just going straight up and going straight back down. But I want you to look at the background. We're not just going straight up and straight back down. We're actually moving along in a horizontal direction. But the okapi looks like it's just going up and coming right back down. So I have a second video that we did a couple of takes here. And it looks, we have that. So we have an idea of relative motion. What's happening in our X direction is totally different than what's happening in the Y direction. So we'll look at the other video. It's a little different. We're still moving across the desert there. And we've got it. And so you hear my other grandson in the background.
All right, jump.
So he's jumped, and it looks just like he's going straight up and straight back down, but you can see that we're actually moving in the window. So we know that we have that independent motion. And so that's what's going to really come out with our vectors, is that we have that independent motion. So let's switch and do some work with some vectors. So I'm going to stop my sharing and start my sharing again. All right, so I have our quadrants here, and this was one of the pre-work assignments that was out there. And we talked about a vector, and we said that the vector started at -3, -4, and we're going to move as the crow flies to our other location here at 1 and 1. I had a little squick in my, but this is our vector here. So like I said, I had a little bit of a squiggle, so we're gonna bold in our original vector so that we can look at it. Now, so our vector has direction and magnitude. Now the magnitude is gonna be how long this is. And this will be a value that we're gonna call a scalar value. So we have that. Now, our algebra books have told us a few things, okay? We can actually do this as a right triangle. So I can draw my right triangle here. And I have my motion in my X direction, and I have my motion in my Y direction. Now, what you can see that I've done with this vector is I've actually broken it up into two components. I now have what we call the X component, and I have the Y component. And if I've added my X vector and my Y vector, I've added them head to tail, and I've actually been able to do this and show that I can break this vector into its individual components. Now, if I'm on my quadratic here, I'm here sitting here with my quadratic, we know that the magnitude of this X component, right? I'm at -3 over here, and I'm at 1 here. So the magnitude of that component, it has a magnitude of 4. And I'm using the absolute value because that's telling me I'm a 4. But if I want to give it direction, that's a +4. Because we're calling this direction as our positive. Similarly, I can do the magnitude of this Y component, and I'm going from -4 to 1. Then I go up 4 plus 1. So the magnitude of this vector is 5. And we can write it as a +5 because I'm now giving it direction. So I've broken up this item and I've given this component. Now we can do a couple of fun things. One is I can call this a vector A. And you guys have probably seen this in algebra. And I'm going to use this vector symbol here. And I'm going to talk about a unit vector I and a unit vector J. Now the unit vector has a magnitude of 1, and it's telling you the direction. So I is in the X direction, J is in the Y direction, and Z would be in the direction if I was in 3 dimensions. So now I can rewrite this vector here. The magnitude of this vector is that I have a +4 and I have a +5. And now I have written the direction and the magnitude of that vector. Now I know it doesn't look like I've written the magnitude, but I have. Because now if this is my right triangle, we can figure out what that scalar is, right? Because I have my a squared plus b squared is equal to c squared. Well, now I have 4 squared plus 5 squared is going to equal my c squared. So 4 squared is 16, 5 squared is 25. And so if I add those two numbers together, and it's after 5 o'clock, so I don't want to get funky, and we always do that. So I've got 41, and then I have to find C. The value of C is going to be the square root of 41. And that's going to be 6.4, whatever my units are. So if I've written this like that, I can find out the magnitude of A, and the magnitude of A is just going to be the square root of 4 squared plus 5 squared. So I can actually do the magnitude of A. Now, what's interesting about vectors is I can say, well, what's 3A? I can multiply this vector by a scalar. So 3 times 4 is 12. And 3 times 5 is 15. So now I have a new vector. 3a is going to look like this. 3a will totally look like that. So that's kind of an interesting piece. I can do a -1, so I can add a -1. So that would be -4, and that would be a -5. And then I can add vectors. So I can do my vectors like this. So let's take a vector. So I'm going to write 2 vectors down. So I'm going to write an A vector is going to be, we're going to make it 5i plus 1j. And I've got a vector B that I'm going to say is -3i plus 2j. So let's go ahead and draw ourselves a grid. And I'm going to give myself some units here. And I'm trying to be as nice and precise as I can. Okay, so I can look at this A vector. So I will go over 5. 1, 2, 3, 4, 5. So there's my 5. So we're going to write that down. And then I'm going to go up 1. So I could write this as my 5, 1, like we would in our algebra book. And I can draw my vector. Now, what's interesting is I can look at this in a different coordinate system. Okay, we can figure out r, which is the length of my vector, and that r, the magnitude of a, which is going to equal the magnitude of r, is going to be the square root of 5 squared plus 1 squared, which is going to be the square root of 25 plus 1. So that's the square root of 26. And if I figure out the square root of 26, that's going to be like 5.1. Okay, so we know r, and we now can figure out this angle. So I could actually write this instead of my x and y coordinates. I could write it as an r theta coordinate. And we can figure out that angle because I know this side is a 1. I know this side is a 5. The tangent of my angle is going to be my y divided by my x. And I can figure out my angle. So that's going to be the arc tangent. And now if I want to make sure that's in degrees, and so I'm going to go ahead and show everybody here that my calculator is in degrees. I can switch from degrees to radians to gradians by working through by working through my calculator. But I'm going to stay in degrees, so I want to stay in degrees. So I have that. So I'm going to do my inverse tangent of 1 divided by 5. And that tells me.
I can't see your calculator. Like
Yeah,
I can see what's on it. Yeah, there you go.
Okay.
Thank you.
And that's where it says degrees on there. So if I do my calculation, I'm going to get my 11.3 degrees. And that looks about right because we know that if I went through halfway, that'd be 45 degrees. If I'm up here, it's going to be 90 degrees. So if I want to add vector A plus vector B, I can add them graphically head to tail. So in this case, we're going to go a -3. So I'm going to go 1, 2, 3. There's my -3. And then I'm going to go up to 1, 2. And so now I've added my vector head to tail. So this is my A vector. This is my B vector. And now I'm going to do this in a different color, just so that we have it in a different color and everything's a little clearer. This is going to be what we call the resultant vector. So this is vector A plus B. All right, that's my vector A plus B. And if I look at this, this looks like it's going to be a 2 because I'm reading it right off my graph. It's a 2 and it's a 3. So I have that right there. I've looked at my components, but look what we can do here. I can add my A plus B. I take 5 minus 3, that's a 2I. I take 1 plus 2, that's 3J. So I've done this now graphically. I've added my vectors. I've done it graphically. And I have done it mathematically. And now I can go in and figure out, well, what's the magnitude of A plus B? Well, that's just going to be the square root of 2. 2 squared is 4 plus 3 squared is 9. That's going to be the square root of 13. And if I do the square root of 13, that's going to be 3.6. And now if I want this angle, that angle, I'm going to do the exact same thing I did here. I'm going to take the arc tangent of my y, which is 3 divided by 2. And my angle is going to come out as 56 degrees. And if I've drawn my picture, it looks like 56 degrees. Now, typically, when we're measuring angles, this is going to be counterclockwise. From the x-axis. So that 56 degrees is counterclockwise from the x-axis. But WebAssign might ask you, what's the angle clockwise from the y-axis? It might ask you that question. Well, if I did that, that's just going to be 90 degrees minus my 56 degrees. And so if I do that, it's going to be about 34 degrees. But that's where it's telling you the direction. So you may end up with problems that look like that. So this is stuff you've done before. You just have never realized it in terms of the fact that you've got that you're looking at it in terms of what we call a vector, because you probably haven't referred to it as a vector. But let's think about it in terms of our motion. Now, most of us have driven in the lovely state of Oklahoma, right? So I've got good old Highway 60 here. And we're going to drive from Ponca City to Tonkawa. And that stretch of road is pretty much in one direction. So we're actually going to be moving at 27 meters per second down the road. Okay. This is a velocity vector. So our direction is going to be a vector. Velocity is going to be a vector. And acceleration is going to be a vector. So they're all going to have vector components to it. Now, we know, and actually today was starting to be that way, we can have a south wind come in, and the south wind may be blowing at 5 meters per second. We can think of this as a boat trying to cross or flowing down a river. Or we can think of it as, we're being pushed down the river. Well, we could ask, well, what's the resultant velocity if I am not actively doing something on this particular, if I'm not actively counteracting the steering, and I'm on an icy road, we know what's going to happen. I'm really going to veer off in this direction. So we can actually do this velocity. So there's my 27 meters per second. Here's my 5 meters per second. And I've got a resultant vector, and this would be, as the crow flies, as my resultant velocity. And we can figure that out. Well, these are nice because my A vector, this is my A vector. My A vector is 27 meters per second in the I direction. And we're going to say it's negative because we're going that way. My B vector is a positive 5 meters per second in the J direction. So my resultant vector is going to be negative 27 meters per second in the I plus 5 meters per second in the J. And now I have a vector that takes into account both the X and Y components. So you guys have done this before. And you've looked at as the crow flies, we give it out of separations. So we can look at this couple of different ways. So let's take a cannon. And now we're going to shoot my projectile out of the cannon at 20 meters per second. Okay, we're going to shoot it out of the cannon at 20 meters per second. But we have our toolkit. Our toolkit says our final velocity, which is a vector, is equal to our initial velocity, which is a vector, plus acceleration, which is a vector, times time. We have our final velocity squared plus equals, this is going to be equals my initial velocity squared plus 2 times my acceleration. But then we have a problem here. I can have a change in X or I can have a change in Y because this is the X and Y's are independent. That's a big or. Okay, that's a big or. And then we have our distance is equal to our initial velocity plus 1/2 our acceleration times time squared. Okay, but we've got our distance. We've only been dealing in 1 dimension, but now I've got something that's going to go to 2 dimensions. And we already know what's going to happen because we've done this before. We end up with an object that's going to do something like that. But we have the X motion and the Y motion are independent. The other interesting thing is my acceleration due to gravity is only in the Y direction. So if I take my toolkit, my final velocity is equal to my initial velocity plus my acceleration times time. My final velocity squared is equal to my initial velocity squared plus 2 times my acceleration times my change in distance. And then I have my distance is equal to velocity times time plus 1/2 acceleration times time. My X motion and my Y motion equations are going to be different. This is just going to say my final velocity is equal to my initial velocity because my acceleration in the X direction is equal to 0. But over here, I get my final velocity is equal to my initial velocity plus my acceleration due to gravity times time. Well, here I get my final velocity squared is equal to my initial velocity squared plus 2 times my acceleration in x times my d. Guess what? That goes away because my acceleration due to x is 0. And then for this one, my change in x is going to equal the initial velocity in the x direction. And these are all in the x direction times time. Now, if I do this for my y, I'm going to get my final velocity squared is equal to my initial velocity in the y direction plus 2 times my g times my change in y. I get my change in y is equal to my initial velocity in the y direction times time plus 1/2. And I'm going to go ahead and put a minus g, and I'm going to go ahead and put a minus g here. Times time squared. Oops, I left a square out. There we go. We got a square. So we can rewrite these into those parts. But what I don't know so far is what is my initial velocity in the x direction and what is my initial velocity in the y direction. Well, that goes back to what we were doing just a little bit ago. I'm going to need a little bit more information, so we're going to actually give ourselves a 30-degree angle. And now I can use my trigonometry to say my velocity in the x direction is going to equal that initial velocity, which is this, times the cosine of my angle. My velocity in the y direction is going to equal my initial velocity, sine of my angle. And if I do that, I'm going to get 20 meters per second, cosine 30 degrees. And this one is going to be 20 meters per second, sine 30 degrees. And I have my components that I'm going to use in those two directions. And this will be 17.32. And that one is going to be 10, and these are in meters per second. So we start to get those different equations. And we can rewrite our equations in terms of x and y. Now, one of the things that one of the pre-work problems that you guys had looks very much like this. And you're going to have a lab coming up that's going to do something very similar. So if I roll a ball off of the table, we know how it's going to respond. It's going to actually look like that. That's exactly what it looks like. If I tell you that it's rolling off the table at 3 meters per second, this is my initial velocity in the x direction. But my initial velocity in the y direction, if it's just rolling off, is 0 meters per second. So I have an equation. If I'm looking to see how far this falls away from the edge of the table, my distance x is going to equal my 3 meters per second times time, which is my initial velocity in the x direction times time. But right now I don't know time. Question mark. But let's say I know the height here. And if I'm in my physics lab, the height is equal to 1 meter. It's 1 meter off the edge of the table. Well, I get so this is one equation. Well, my y direction is going to equal my initial velocity in the y direction times time minus 1/2 gravity times time squared. That's my second equation. So I get my height is 1 meter is equal to minus 1/2 9.81 meters per second squared times squared. I can solve for time. plug that back up into here, and I can solve for distance. I get two equations, two unknowns, because I have independent motion. Independent motion. So that gets us started with this. I don't want to dive into those projectile motion problems yet, because I want you to have the opportunity to do your test. But this gets us into where we were headed. But you're going to have your equations of motion written into your X and Y components, and we can split that up from our vectors. We can use our vector notation here to be able to describe our motion in order to give us our magnitudes and direction. So hopefully that gets you guys started on your chapter 3 homework. It should give you enough to be able to do the couple of vector problems that are on the test. And then everything else is coming from chapters 1 and 2. So I'm going to hit stop recording here.